Now we go down to the memory. Let's see a node in memory, where it sits, how many bytes it takes, and why the order lives in the pointers. Nodes can sit anywhere in memory. Let's give them real addresses and see what holds the list together. These are the three nodes. On purpose they sit out of order. Node 10 is at address hex 3000. Node 20 is at hex 7000. Node 30 is at hex 4200. Now look at the next fields. Node 10's next holds hex 7000, which is node 20's address. Node 20's next holds hex 4200, node 30's address. Node 30's next holds null. So each next field stores the address of the next node. The addresses are scattered, but the order 10, then 20, then 30 comes entirely from the next pointers. And remember, teaching addresses like hex 3000 are just for the picture. Real malloc gives you unpredictable, non-consecutive addresses. This is our first structure built on real pointers, so let's define one bridge now. The tail's next field holds nothing, and nothing has two names in this course. On the left is the pseudocode, this traverse of head. We set cur to head. While cur is not null, we visit cur.data, then we set cur to cur.next. In pseudocode, we write this end marker as nil, which just means no node. On the right is the same loop in CA for loop. We start with node star cur set to head. We keep going while cur is not null. Each round we do cur becomes cur arrow next. Inside, we visit cur arrow data. In C, the end marker is spelled null. This is the rule lot for all 21 chapters. Pseudocode nil is exactly C null. A next field holding null is a link to nothing. That is the end of the list. Later, a search that returns an index will use -1 for not found. That is a separate sentinel, not null. Let's zoom into one node byte by byte. On a 64-bit machine, one node takes 16 bytes. This is the node holding 10, at base address hex 3000. This is the key memory map for the whole chapter. The whole block sits on the heap. This band marks it. It is one node struct, laid out from low addresses at the bottom to high addresses at the top. At the base, hex 3000 is the data field. It holds the value 10. The int takes 4 bytes. Next, at hex 3004 come 4 bytes of padding. They are empty. We need them so the pointer that follows starts on an 8-byte boundary. That is called alignment. An array cell had no padding, but this node does. On top, at hex 3008 is the next field. It holds hex 7000, the address of the next node. The pointer takes 8 bytes. So 4 for the int, 4 of padding, and 8 for the pointer gives 16 in total. One thing to keep straight. The next field is not the successor node itself. It stores the address of the successor. The pointer is the extra cost we pay to stop storing nodes next to each other. Now let's lay the 3 nodes out by address, the way they might really sit in RAM. Top to bottom is address order now. And notice, it does not match the list order 10, 20, 30. Each next field holds the address of its successor. Here we show that with matching color instead of an arrow. Node 10 sits low in memory at hex 3000. Its data field holds 10. Right above it, at hex 3008, is node 10's next field. It is pink, and it holds hex 7000. That is the address of node 20. Follow that pink link up to the top of the map. At hex 7000 is node 20's data field, holding 20. Just above it, at hex 7008, is node 20's next field. It is amber, and it holds hex 4200. That is the address of node 30. Follow the amber link down to the middle. At hex 4200 is node 30's data field, holding 30. And its next field, at hex 4208, holds null. That marks the end of the list. So in address order, hex 7000 is highest. then hex 4200, then hex 3000. But the list order is still 10, then 20, then 30. Node 10's pink next names node 20. Node 20's amber next names node 30. These color-matched links are what make a structure linked. Now the full picture. Head lives on the stack. The malloc nodes live on the heap. It is all one address space, drawn from high addresses at the top to low addresses at the bottom. Up here is the stack. This band marks it. This is where your local variables live. Here on the stack is head itself, at address hex 7FFD0028. Head is pink. Its value is hex 3000. That is the address of node 10, down on the heap. Lower down is the heap. This band marks it. This is where the nodes were made with malloc. And here is node 10, at hex 3000, holding the value 10. That is exactly the address head was pointing to. So head on the stack reaches across into the heap. Lose head, and you leak the whole chain. A quick learning check. Suppose a bug sets node 20's next field at hex 7008 to null. What does traversal from head print, and what happens to node 30? Think about it before we reveal the answer. This is the answer. Traversal prints 10 and 20, then stops. The early null reads like the tail, so the walk ends there. Node 30 stays allocated, but now nothing points to it. It is unreachable. That is a memory leak. These few expressions are the number one source of linked list bugs. Let's keep them straight. In this example, head is stored at stack address hex 7FFD0028, and head holds hex 3000. First, head on its own. This is the pointer variable's value. Here it is hex 3000, the address of node 10. Second, star head. The star means dereference. It gives you the node it points at. Here that is the struct holding 10 and hex 7000. Third, head arrow data. This reaches into that node and takes the data field. Here it is 10. Fourth, head arrow next. This takes that node's next field. Here it is hex 7000, the address of the following node. Fifth, ampersand head. The ampersand means the address of. This is the address of the head variable itself. Here it is hex 7FFD0028. That is a different address from everything else. Two things to remember. Head arrow next is just shorthand for star head in brackets dot next. You dereference, then take the field. An ampersand head is a completely different address. It names the box that holds the pointer. We will need it later to change the caller's head.